Chapter 11 Kinetic Theory of Gases, Section 11.5 Mean Free Path. The mean free path is defined as the average distance a gas particle travels between two successive collisions. It's denoted by a Greek letter lambda. Now let's look at this graph to see how we can determine the value of lambda. So this red sphere is colliding with this green sphere, changes its direction, collide to the second green sphere, the third one, the fourth one, and the fifth one. And now this mean free path is just the average of lambda 1, lambda 2, lambda 3, lambda 4, and lambda 5. And over here we have an equation, the sum of all those segments divided by the number of segments. And also you can see the number of segments is equal to the number of collisions. 1 collision, 2, 3, 4, 5. 5 collisions, 5 segments. So really the average distance is the total distance divided by the number of collisions. The total distance is the sum of all those lambdas. 5 of them, we sum it up and divide it by 5. But if we are looking at a certain time period, then lambda is simply the total distance this particle has traveled within time interval delta t. On top, on the bottom is the number of collisions in delta t. And again, the number of collisions in delta t is equal to the number of segments over here. You can see 5 collisions, 5 segments. Now on top, it's just the average speed of this particle times delta t. On the bottom, it's the collisional frequency of the particle multiplied by delta t. Delta t and delta t cancel. On top, we have the average speed of this particle. On the bottom, we have the relative average speed. So over here, when we derive the collision between two type 1 particles, we need to use this v sub 11 here. That means the relative average speed between type 1 and type 1. Sigma is the collisional cross-section area. N1 over V is the number density. So we have this equation in the end, because the average relative speed is the square root of 2 times the average speed. So we have this equation. We can further express this equation in terms of pressure and temperature, because very often the temperature and pressure are given. So lambda is equal to 1 over the square root of 2 times sigma, the collisional cross-section area. And over here we simply express the number of particles as the number of moles times the Avogadro constant. We rearrange this equation. We see V over N1 on top. Well, using ideal gas law, it's just RT over P. So we get this expression. And this expression is equal to this expression because R over NA is the Boltzmann constant. So in the end, it can be just the Boltzmann constant times temperature divided by the square root of 2 divided by sigma and P. The mean free path is inversely proportional to the collisional cross-section area, sigma. It's understandable because if you have larger particles, you have more frequent collisions, and that will make the lambda smaller. It's also proportional to the molar volume of the gas. Over here you can see the molar volume, because if you have a larger molar volume, it's hard for a particle to find another particle. It has to travel a longer distance to encounter another particle. If temperature is held constant, then lambda is inversely proportional to pressure over here. But if pressure is constant, then lambda is just proportional to the temperature. So either way, you can express lambda as a function of molar volume or as a function of temperature and pressure. Depending on what information is given to us, we can use any one of those equations. They are all correct. They are equivalent to each other. Now let's look at one numerical example problem, 11.5.1. Let's calculate the mean free path of argon. Sigma is given. This is the collisional cross-section area, 0.36 nanometer squared. By looking at this, you can probably understand the radius of argon can be computed by pi r squared equals this, roughly. Now we're given pressure and temperature. Let's calculate the mean free path. So in the previous slide we have a bunch of equations, but since temperature and pressure are given, we'll just use this equation. We have Kb on top, T on top. On the bottom we have pressure here. We have sigma in meters squared because we want to use SI units. The result is 80 nanometers. So on average, between two successive collisions, an argon atom has to travel about 80 nanometers. What if we have a lower pressure? Let's keep the temperature constant, drop the pressure to 0.1 atm, and you can see lambda becomes 800 nanometers. Well, it's just because lambda is inversely proportional to pressure when temperature is held constant. Now let's look at example problem 11.5.2. We're calculating the mean free path of helium with a smaller collisional section area at 1 atm and 298 K. So same equation, 130 nanometers. We can compare this to numerical examples. Over here we have a smaller collisional cross-section area. That makes it hard for the helium to collide with another helium. It's a little bit harder than this. Alright, just imagine in a room you have blindfolded birds flying around. If the birds are really big, they will collide very often. But if the birds are very tiny, like hummingbirds, so even if they just fly in random directions, it's hard for them to collide with each other, only because the sizes are small. Their collisional cross-sectional area is small. So that's why we have a longer mean free path. So again, just by looking at the equation, you can see lambda is inversely proportional to the collisional cross-section area. Again, just to emphasize, this lambda is proportional to the molar volume. If you have a larger volume, that means the particles are farther away from each other, and then you of course will have a larger lambda. If the molar volume approaches infinity, well then lambda approaches infinity.